in the last lecture, we have discussed the few theorems, the Cauchy's theorem of first kind and Cauchy's theorem of the second kind, where we have developed some results which will help in getting the limit of the sequence A n. And remember that Cauchy's theorem, Cauchy theorems, that is, if the sequence A n, if the sequence A n of real numbers converges to L, then the sequence A 1 plus A 2 plus A n by n, this sequence will also converge to the same point L, and we have seen the proof for it. That is, a sequence converges to L will imply the convergence of the sequence of their means, arithmetic means. The converse of this is not true. Converse of this result is not true in general. That is, a sequence A n for which this A 1 plus A 2 plus A n by n will go to L, but sequence A n may not go to L. For example, if we consider the sequence A n as 1 plus minus 1 to the power n divided by 2, we take this sequence. Obviously, the sequence A n tends to, when n is, let us take this minus sign, let us take this is minus sign or minus, take the minus sign 1 minus 1 to the power n. So, if the sequence, if we choose the sequence A n as 1 minus 1 to the power n, then as n is even, then this term becomes positive and this is minus. So, A n will go to 0 along even ends. When n tends to infinity, then along the even direction, and when n is even and tends to infinity, then it will go to 0. While when n is odd, then this becomes minus plus 2 and this will go to 1. So, limit of this sequence does not exist. So, limit of the A n as n tends to infinity does not exist. We do not have a single limit here. However, if we consider the A 1 plus A 2 plus A n by n, then this comes out to be, say, when n is odd. So, when you take n is odd, then A 1 becomes this is plus 1. So, 1, A 3 becomes again 1, because A 3 is this minus plus 1. So, 1 plus 1 this will go, and total values are, when n is odd, n plus 1. So, it will go to the n plus 1 by 2 and then divided by n. So, it will go to the tends to this as when n is odd. When n is odd, you are getting this value, and when n is even, then it will be n by 2 into 1 by n. So, in both the cases, so as n tends to infinity, this sequence A 1 plus A 2 plus A n by n, this will go to half, because here it is clearly half, and when you divide by n, then you are getting 1 plus 1 by n by 2, which n tends to infinity, it will go to half. So, limit exists. Okay. So, here the Cauchy theorem, one side is true, that if A n converges to L, then the sequence of their mean values A 1 plus A 2 plus A n, sequence of the means will go to the same limit L. Similarly, when you go for the second result of the Cauchy, the second result of the Cauchy says that if a 1, a 2, a n, this is sequence, if n be a sequence of the positive number, where if n's be a sequence of positive numbers, and limit of a n plus 1 y a n as n tends to infinity exist n equal to L, then limit of the a n to the power 1 by n when n is sufficiently large will also L. The converse is again converse is not true in general. For example, suppose I take the sequence n's equal to 1 if n is odd and equal to 2 if n is even. Then a n to the power 1 by n. This limit is as n tends to infinity, basically a constant to the power 1 by n, and as it is sufficiently large it will go to 1. So, limit will go to 1 exist, but the limit of this a n plus 1 by a n, if I picked up this thing, then what happens is then when n is odd, the value this will be even. So, this will go to 2 by 1, and if n is here even, then it is odd. So, this is even. So, it will go to half. So, basically the limit will go to as n tends to infinity, the ratio limit does not exist, because it keeps on jumping, does not exist. And this shows the converse is not true. Okay. So, here these two examples which we have discussed. Let's now we will give few more results which are useful for that. So, let us see the first is fundamental theorems on limit. On limit of the sequence of real numbers. Okay. So, what this theorem says, if x n and y n be the sequences of real numbers, if x which is a sequence x n and y which is sequence of y n, if x n y n be the sequences of real numbers, that converges to the real point x and y respectively, and let C be any constant R, C belongs to R, real number. Then the sequence x n plus y n, x n minus y n, x n into y n and C x n and C of x n will converge or converge to x plus y, x minus y, x into y and C into x respectively. Okay. So, let us see the proof. Proof is very simple. We have already discussed the proof while considering the sequence of rational numbers and in terms of the Cantor's and Dedekind's case. So, let us see one of the proof of the suppose x n and y n are convergent, given suppose x n converges to x, y n converges y, this is given. So, for a given epsilon greater than 0, there exists n n 1 n n 2 which depends on epsilon such that mod of x n minus x is less than epsilon for all n greater than or equal to n 1 and as well as mod of y n minus y is less than epsilon for all n greater than n 2. Let us take this. Now, choose the n, choose say n naught which is the maximum of n 1 and n 2. Okay. So, there is n 1 n 2. So, consider mod of x n plus y n minus x minus y. Now, this is less than or equal to x n minus x plus y n minus y. Now, when n is sufficiently large greater than n 1, then this part is less than epsilon. When n is sufficiently large from n 2, this part is less than. So, when you choose n to be greater than n naught, then this is less than epsilon plus epsilon for all n greater than n naught. Therefore, the sequence x n plus y n will converge to x plus y, and that proves the things. Okay. Similarly, now, if we take other parts, say second, similarly x minus, similarly for x n minus y n, this sequence will go to x minus y. Proof will be the same. Then for x n y n, let us take this sequence. Let x n given x n converges to x and y n converges to y. X n converges to x and y n converges to y. So, we wanted to show that this is less than equal. Okay. So, consider x n y n minus x y mod of this. Now, this will be less than equal to x n y n minus y mod of this plus mod of x n minus x into y, just by adding and subtracting and applying the triangular inequality, which is less than equal to mod x n mod y n minus y plus mod y mod of x n minus x, let it be 1. Okay. Now, since our x 1, since the sequence x n is convergent sequence, so it is bounded. So, there exists m 1 greater than 0 such that all the terms of the sequence is less than equal to m 1 for all n, because it is a convergent sequence. So, it must be bounded for all n. Let us suppose capital M is the maximum of m 1 and mod y. So, we can choose this thing like this. Now, further this part from 1 we get mod of x n y n minus x y is less than equal to, this is less than m into mod y n minus y, plus m into mod x n minus x. Now, y n and x n both are convergent sequence. So, for a given epsilon, since x n converges to x, so for given epsilon greater than say 0, there exists some k 1 depends on epsilon such that mod of x n minus x can be made as small as you please. So, suppose I choose the smaller number as epsilon by 2 n. Similarly, y n converges to y. So, for the given epsilon greater, there exists k 2 which also depends on epsilon such that y n minus y is less than epsilon by 2 n. Okay. Now, once you have this, then you choose the k as the maximum of k 1 and k 2. Let us take k to be k 1. Then if x 1, so for n greater than equal to k, for this number what happened? Use the from 2, we get mod x n y n minus x y is less than equal to. Now, this is less than equal to epsilon by 2 m. So, basically this is epsilon by 2, this is less than epsilon by 2, but this is true for n, there exists k 1 such that this is true for all n greater than k 1, and this is true for all n greater than k 2. So, if I choose the k as a maximum of k 1 and k 2, then both the results are true for n greater than k. So, when choose n greater than k, then this is less than epsilon by 2, this is also less than. So, this is less than epsilon from 2. Okay. So, this shows that x n y n converges to this. Okay. So, this implies x n y n, this sequence goes to x y as n tends to infinity. Okay. So, this will be okay. Similarly, when you take the third, say c of x n, in a similar way you can do it. Otherwise, by n you can consider as the constant c. So, by n a sequence c and it will converge to c x as per this. Okay. Now, if the sequence, another result is if x n and y n and this result let it be a, this is the fundamental a. So, let next result is b. If sequence x n converges to x, if sequence x n converges to x and z n is a sequence of non-zero and z n is a sequence of non-zero real numbers that converges to z, say z, and if z is not equal to 0 and if z is not, then the quotient sequence x n over z n will go to x over z as n tends to infinity. That is the limit of this sequence over divided. Again, the proof is can be followed with the epsilon delta definition, and the proof runs as it is as follows. Let us suppose z n is a sequence of the number which is given non-zero. Let us suppose let alpha is half of mod z, where z is the limit of z n which is given non-zero. This is given. So, let us pick up the alpha like this. Okay. Now, since z n converges to z, so for a given epsilon greater than 0, there exists a natural number or integer, there exists a natural number or positive integer k 1 such that mod of z n minus z, mod of z n minus z is less than alpha, okay, is less than alpha. Now, this implies that z minus alpha is less than equal to minus z n minus z, which is less than equal to mod z n minus mod z for all n greater than equal to k 1. Why? Because this is true such that for all n greater than k 1, we have this thing. Now, if I take minus sign, then minus alpha is less than this, fine. Now, apply the triangular inequality. So, what you get is mod of z minus, because z 1 minus z 2, mod of this is greater than equal to mod z 1 minus mod z 2. This result is true. So, using this result, we get this part. Okay? Now, half of this z. So, what will therefore, what will be the mod z minus alpha? Bring it here. This is greater than equal to mod z, less than equal to mod z n for n greater than equal to k 1, but z minus alpha, alpha is mod z by 2. So, it is basically half of mod z. So, when it is sufficiently large, the sequence of the term mod z n is greater than equal to half of mod z. Okay. Now, use this one, this is say 1. Okay. Now, consider mod of 1 by z n minus 1 by z. Now, this can be written as mod z n minus z over mod z n mod z, but mod z n is greater than this number. So, it is less than equal to 2 over mod z square into mod z minus z n, and this is true for all n greater than equal to k 1. Now, as z minus z n goes to 0, because z n sequence converges to z. So, for a given epsilon, now for given epsilon greater than 0, given, we can find there exists a natural number, a positive integer k 2 such that if n is greater than equal to k 2, then mod z minus z n, this sequence less than the number epsilon mod z square by 2. This is a smaller number. So, since z n converges to z, so we can identify this thing for all n greater than k 1. Okay. Now, this is true for all n greater than k 1. This is true for all n, sorry, all n greater than k 2. This is true for all n greater than k 1. So, if I pick this is 2. So, let it be 2. So, if we want to 1 and 2 combine, then what happens is that this k, if I take k, a integer which is maximum of k 1 and k 2, then this difference can be made less than epsilon for all n greater than equal to k, because both these are true, and this shows the sequence z n 1 by z n goes to z. Therefore, limit of the sequence 1 by z n as n tends to infinity is 1 by z. Okay. let it be 3. Now, we are interested in x n by z n. So, it is the as good as x n into 1 by z n. So, the sequence x n into 1 by z n will go to x into 1 by z, that is the answer, because of the product of the two sequence. This is product of the two sequence will go to this. Okay.